So we'll get started in just a second. I'm going to try and do a couple more self-check questions today live. We'll see how that goes. Thank you. All right. Okay. All right, so I realized that the Snap project link on the slides is broken. So I'll edit that really quick and get started. So today we're going to talk about algorithmic complexity and how we analyze algorithms. And so where we started off last week was we want to solve, we had algorithms which enable us to solve a computational problem, and they give us sort of a defined set of steps for how we do that. And there are many ways that we can solve a particular kind of problem. So the question then arises, which of the algorithms that we have is a better option? Or if we're given multiple different algorithms to solve the same task, how might we decide which one should we use? So we're going to take, let's say 30 seconds to a minute. And the first question on Gradescope, there are going to be a lot of these today, so I'm going to go through some of them kind of quickly during lecture. If you don't get a chance to answer them, they will of course be available after the fact. But if you could open up Gradescope, this will be question number 1 right now. I'm going to pull up the results. Answering. So let's see, how many submissions do we have so far? So let's wait a few more seconds. Let's give everyone a chance to pull it up. We'll try and go through most of these during lecture today. We might not get to all of them. So as folks are voting, it looks like, let's see, what does that say? Yeah, cool. So far about 80% have the correct answer, which is in the lab, we were given 2 ways to find a number in a list. Which algorithm would generally take less time to complete the search as the description now it's of course on the wrong screen. Come on. There you go. Oh, it's just not showing up. So in this case, the answer is B, the binary search algorithm would generally take less time to search. And so how do we figure out that binary search is in fact faster than this other algorithm that we're just going to typically call linear search? So in the set of slides, we've updated the blocks that are linked in the Snap project slightly differently, just so they'll be a little bit more clear. Let's sorry. Okay. So we have a few different blocks in this case. And this project, I've updated things a little bit from the slides to use a higher order function to time a block instead of resetting the timer. It works the same way, but I think it's a little bit cleaner in terms of what will be said. So how long does it take to find the number 1 in the list? In this case, that's like pretty quick, 0.02 seconds. How long? Now 0.001. How long does it take to find 1 in a list using binary search? This time it's taking a little bit longer. So for each of these blocks, right, you can see, well, if I'm just looking for the number 1 in this list of 300 numbers, it actually seems like binary search is taking a little bit longer. Now, what if I ask for something like the number 301? So this is going to say, how long does it take to find 301 using linear search? And this is taking a little while. So in this case, we have about 4.9 seconds, pretty close to 5. Whenever we're doing measurements like this, it's probably a good idea to run things multiple times just to get a sense. So again, 4.98, that's pretty close to 5. Now let's run 301 in binary search, under a second. Let's run this a couple times, under a second again. So each of these algorithms, right, is giving us pretty different results for just doing a simple task like finding a number in another list of numbers. And if you wanted to just use the block on its own, right, this block, again, just reports whether the number is in a list. I've actually given 3 different versions of this block. We're not going to look at the one that says primitive. That uses Snap's built-in find block. So it's illustrating the point that if you want to play with this project, there are many ways to implement an algorithm. So what's going on here, right? In our first list, where we say is number 1 in our list, it actually turns out that our linear search is quite a lot faster. And if we think about how we might build that block that we talked about last week in lab, it turns out that like searching for 1 in this set of lists is pretty easy, right? Because if we go back, and actually let's just go back to Snap really quick. If we look at a list of numbers, just turn the watcher here. Why is number 1 so easy to find? Well, it turns out that number 1 is the first item of the list. So if we say, how long does it take to find number 1 in the list of numbers? And the list is a number list, yeah, that's in order starting with 1. We could say, well, 1 is going to be very easy to find because it's the first item in our list. When we think about analyzing our algorithms, we're going to talk about what these terms mean. We can say this is the best case, right? The very first thing we do, regardless of whatever algorithm it might be, is 1 is hitting the nail on the head. We found the thing, we got the answer, and essentially 1 step, right? Is item 1 equal to 1? We're good. Of course, what might turn out to be, though, is that in the real world, we're often not going to be working with this best case. When we want to, let's say, find a number in a list, we have to consider the fact that we might be searching for a number that's never in the list. So in a list of 300 numbers, searching for 301 means we have to check every single item in the list before we find that 301 is not on that list. This might be any kind of algorithm where we're trying to compute something, right? If we're looking at even just finding, let's say, the median value in a list of numbers, how long will it take to do that? Well, our list of numbers could be really short, our list of numbers could be really long. So our goal is to think about how long will it take to solve a question regardless of the particular type of data that we're working with. So the worst case also, is one of those things where the system that we're building, right, we have to protect against that. So if Gmail has a search function and it's trying to search through all your thousands of email messages, obviously we always want that to be fast, right? But what if the worst case to find a particular term ends up being ridiculously slow, and it takes something like tens of minutes or hundreds of minutes to execute a particular search because the query or the terms that you're trying to search for just happen to be really bad for this algorithm? Well, that's pretty unacceptable because you might not be able to find to find that set of emails. And it turns out, for reasons that we're not really going to get into, but on average, the worst cases happen quite a bit more often, and the average sort of running time of an algorithm tends to look a lot closer to the worst case performance. So when we're looking at lists of like 300 numbers, we can see some interesting differences, but in the real world, the average or the worst case tend to look very similar to each other. So what we're going to do today is focus on what happens in the worst case of all of these algorithms. What is the worst possible outcome that can happen when executing this function? And so how do we then formalize what that is? So in this case, again, this is the block that I renamed linear search. So searching for 301. The nice thing about Snap, by the way, is I was going to do this slide, but we have kind of a lot to get through. So these were the results from the last few runs of the block last semester, but the numbers turn out to be pretty consistent. On those computers that are relatively modern, this block will take about a little under 5 seconds to find one value, or actually to find 301 in the list of 300 items and tell you that it's not there. And this seems pretty slow, and this should seem pretty slow to you. So does it really seem reasonable that this is the case? Well, it turns out, no, in general, it's not super reasonable. Computers are, if nothing else, very good at dealing with numbers. What Snap is actually doing here is intentionally slowing down the way that things work, such that if you're drawing something like in our first few labs, when we draw squares, labs, when we draw fractals, Snap does a whole bunch of things to make that drawing and animation a lot more smooth. It does some of the slowing down to make performance consistent from computer to computer, so that if you were to publish a game on like the Snap Cloud, anyone can open that game and then they could expect it to work in a similar way. And in Snap, I'm not going to go into all the details, but there are just a couple blocks that are worth knowing. Is that if you want to see how things get sped up, there's this block called warp, and warp tells Snap, hey, I'm not doing much drawing, so really speed this up, make it go as fast as possible. Don't slow any code down. And then there's also this option turbo mode, which also changes how Snap does drawing and can speed up computation a lot. So in your own projects, turbo mode and warping, they're never going to change whether or not something is correct or incorrect, but they will speed up certain types of operations, especially if you're manipulating numbers and lists and things like that. So we're not using them today to sort of illustrate the full difference in the time that it takes to compute something. So what else might we say about this list? Well, if our list was even longer, right, something like 1,000 items, these times might take quite a bit longer. In this case, we went from 5 seconds to, in some testing, 16, 17 seconds. This actually makes sense for our block, right? We said it was going through each item one by one. It's a list of 300 items. If we make it a list of 1,000 items, and we say that the time goes from 5 to 17, that's about 3 1/3 times longer, give or take, of some fractions of a second, longer than 5 seconds. And our list is 3 1/3 times longer than our input. So in some sense, what this block is doing makes a lot of sense, right? We double the length of our list, the time that it takes to run doubles as well. And intuitively, if we think about what this block is doing, it checks every item. That makes a lot of sense. And we'll talk about how to formalize that. So some of these results are also inconsistent by a little bit, right? They're not always exactly the same. They jump around. They're within, I would say, in this case, a margin of error. But what can also happen is that our computer isn't just using Snap. So right now, if you're on your computer, right, it's managing Zoom, probably another tab for Gradescope. Maybe you're doing something like have a video running in the background, or running a project in another tab. All of these things affect the resources that your computer can use. And so at any given time, your computer might want to finish a computation before it continues on and says, hey, Snap, now it's your turn to do some computation. So if we start using a clock timer like we've been doing, we'll always see a little bit of inconsistency. Behind the scenes, your computer hardware is also doing a lot of work to try and sort of hide some of these limitations, such that when you execute a Snap program, it seems like it's just running right away, that when you have multiple pieces of applications running on your computer, that they all run seamlessly, and we don't really have to think about the fact that what a computer is really doing is millions of times a second switching tasks as rapidly as it can. So for the most part, we don't have to necessarily consider the fact. If you take 61C, you actually get into the math of how computers store and organize information and the speed at which they can copy information back and forth, and how that affects things. So there's a lot more detail that could be done here. So so in an experiment, right, we might want to say, run these two things side by side, and then see who's faster. And of course, for the set of input, we'll say whatever is faster. Let's say, that algorithm could be the winner. So we can show in this case that this binary search algorithm, because on the case of 301, it completes in a fraction of a second versus the linear search algorithm completing in in about 5 seconds, that binary search is faster. And we call this empirical analysis, because what we're doing is we are running the code, we're getting a timer, we're testing it out, and we are gathering data that way. So this is a valid way, of course, to analyze algorithms, but it has some downsides. So what we're going to do now is look at how we can theoretically analyze an algorithm's performance. And we want to do this for a lot of reasons. So for our binary search algorithm, we can implement it. It's a little bit tricky to implement, but it's not terribly complicated. With some reading and a couple hours of work, I think you all could spend time looking at how it works, figure out the edge cases, go through and even if we didn't have a lab on this kind of stuff, you're at a place where with enough effort you could implement binary search. But there are also a lot of algorithms that we don't necessarily know if they're correct, or they might take a long time to implement, and we still want to understand how they could theoretically perform. And so what we're going to look at is this technique called orders of growth to characterize the time that it takes for an algorithm to execute based on the inputs that we might give that algorithm. So we kind of call this the one true way that computer scientists analyze algorithms. If you like this stuff, Computer Science 70 gets into this. CS10 spends a lot of time on this, and CS170, if you decide to major in computer science, is a course dedicated to the analysis of algorithms. And these are pretty important things because the algorithms that get developed get used all over the place. Binary search as an algorithm is incredibly useful for being able to do things like find data on your computer or in your email inbox efficiently. It's not structured in quite the same way, but those types of algorithms are used in many different places. So one thing that we'll need to consider, right, is we've been testing on just a couple data points. We've been testing in the number 1 and the number 301. For our data set, they represent some pretty interesting cases, right? They represent the first number in our list. They represent a number that's not in our list. But what if our list is much larger, like we alluded to? What if it's 400 items, 500 items, 5,000 items? How does the performance of our algorithm change if the size of our list changes? So what we're going to do is make a plot of our functions, and we've sort of picked plots in lab when we ask a question about this on the quest. We're not going to actually, or on the midterm, we're not going to actually have you draw the plot, but we want to think about this in the sense of plot. So given some input in this case, we're specifically considering the input, the number list. So n is the size of our list. And I'll say we're using function notation here, so R of n is the runtime of our function with respect to the size of n. And there'll be a little bit of math in here, but this is probably the most mathy that CS10 will get. So if math isn't your thing, that's really cool. In this case, for this version of the function, we can run a test. Actually, the way that this is written, as long as our list never has an empty item, this will always run through every item in our list to say that there's no empty item in there. So for 250 items in one test, this took 1.4 seconds. For 500 items, 2.8 seconds. For 1,000 items, 5.7 seconds, and so on. And what we can see is if we graph this list, where we have the number of items in our list on the bottom and the time that it took on our y-axis, we get this line that sort of describes the performance of our list. And what we might notice is that if we were to double to 2,000 items, and then again to 4,000 items, right, we have enough of a trend here that we can expect to understand what's going to happen to our algorithm. So here this is done. Again, these are timed results using empirical analysis, but we're able to actually look at the code and come up with the same graph without necessarily timing our code. So so if you just say, so this is the next question on Gradescope. So if we were to say, as a function of n, what kind of function most clearly models this graph? So think about what the graphs of these functions might look like. Which one of them is closest to this function? We'll go through the next few of these relatively quickly. All right, let's take a look at this. We'll give another few seconds. So as I'm explaining this, the number of correct responses is jumping up by quite a bit. I can't tell exactly how many people haven't responded to just this question yet. But awesome. The number of correct responses is trending in the right direction. If you look on Gradescope, actually, the block name kind of gives a hint to the correct answer. Okay. Well, so this is a linear function. It is that means that C is the correct answer. If we say R of n is equal to n, that is essentially the line y equals x. That is just a straight upward diagonal line where for every step x increases by 1, y would also increase by 1. And what this basically suggests is that for every single item in our list, we take one additional step of time to be able to compute this function. So this is a different function that we don't necessarily know anything about right now. Looking at this function, this is question 3 on Gradescope. How much what would we say is the closest function to this graph? So again, is it square root of n, log n, n squared, or 2 to the n? All right, and looks like people are answering. All right, as people are answering, the correct answers are coming in, which is good. Great, good. All right, cool. So again, we're going through this pretty quickly, so it's okay if there are questions. But yeah, so the correct answers are coming in, and this one is n squared. So what it's essentially saying is for if I go from one step in my function, right? Let's say we start at one item, and that takes one amount of time. 1 squared is 1, and now we double that list to 2 items. Now it's going to take 2 squared amount of time. So going from 1 to 2 is actually 4 times longer in our list. And looking at these times, they're not perfectly squared multiples, but they're roughly that, right? 100 items is 1 second. Going from 100 to 200 is 4 seconds. So doubling our list is 4 times longer now. So that's the equivalent of 2 squared. Going from 100 to 300 is 3 times longer, but our output time, if we look at this, is again about 9 times longer. So on average, we can say that this function looks like n squared. So what we can say then is that we can characterize the order of growth of our function as one of a few different kinds of categories. So at the very bottom, we haven't seen any algorithms that we could classify as algorithms yet that necessarily are constant time, but constant time is sort of we could think of it as like the holy grail of an operation, right? No matter how big my input gets, this thing always takes the same amount of time. And then, I wouldn't necessarily call this an algorithm, although the block is a little bit more complicated than you might expect. The block item 1 of list, right? Getting the first item of a list, that thing is always going to take constant time. Whether the list is 1 item or many items, finding the first item in our list is always going to be a really easy task. So there are many things, in fact, that do take constant time, but they're usually single operations. We have algorithms that are logarithmic. So we'll talk about some of those in a second. I don't want to spoil another question about what some of the awesome logarithmic algorithms are. We have linear time algorithms, and that's what we'll spend a lot of our time writing and working with, essentially things that go through every item in the list. There's a whole class of algorithms called linear arithmetic or linear log algorithms. We're not going to talk about any of them in CS10, but if you take CS61B, there's so many linear logarithmic algorithms, and you can see that they're like on this graph, they're not quite as good as linear time algorithms, but they're pretty darn good. And there's a whole class of algorithms that really, we can in some ways say, make the world work because of this relationship. There are quadratic algorithms. we can roughly think of these things as going through the same list n times. We'll look at another example. And some algorithms have exponential growth where adding just one item to our list doubles the amount of time that it takes for an operation to be computed. And then any mathematical function is technically a valid runtime. So the factorial function could be a valid runtime. That grows incredibly quickly. So we're not going to look at any of those. But here's a good question. So comparing just any two algorithms in the abstract, this should be now question 4 on Gradescope. Comparing any two questions in the abstract, which is faster? Is a linear algorithm faster, one that's shaped like a line, or is a quadratic algorithm faster, one that's shaped like a parabola? All right, we'll give a few more seconds to answer this question. And cool. So the correct number of responses is actually ticking up more quickly than I would have expected, because this question is definitely kind of a trick question. In the abstract, if I say which algorithm is faster between a linear time algorithm and a quadratic time algorithm, it actually really depends on what we're talking about. If I just say which is faster, we don't necessarily know why, because if we were to graph these two functions, r of n equals n and r of n equals n squared, there's a point in time where, for let's say particularly small amounts of n, where n times n could be faster than some additional factor. What's also complicating this graph is something that we haven't really talked about yet, but was referenced on a previous slide, is that when we're looking at orders of growth, I'm really interested in what is this main factor. Is it 1 times n? Is it n? Is it n squared? Is it, we're not going to talk about n cubed. But if there's a multiplier in front, we're not really going to consider that, because as the data set grows large, that multiplier factor doesn't really change very much. So the revision of this question is, which of these is faster for then an extremely large n? And we'll go for this one a little more quickly. Cool, so not too many people have answered yet. Let's see how. All right, let's see what we're looking at. Oh. Awesome. Okay, so the correct responses are indeed coming in. In this case, come on. Where's my mouse? There you go. Yeah, so in this case, the linear algorithm is definitely going to be faster as n gets very large. And this is why typically when we talk about orders of growth, what we're thinking about is that worst case performance as n gets really big. And it doesn't take much to see that this green line, which is the algorithm, after this point right here, right, it's just always going to be lower than that blue line. It's growing, like, you know, if we make our n many times larger, the function is going to take longer to compute, but at some point n times n is just going to be so much larger than what this happens to suggest is this function would be 30 times n. And so when we analyze our algorithms, we actually don't care about this first term. Whatever constant factors we have, we just drop those when we consider something. If it's 30 times n, if it's 100 times n, even if it's like 1,000 times n, that's still a linear time algorithm, because as that number gets bigger, that constant factor just really doesn't matter. So generally, when we're talking about orders of growth, we really only care about that worst case performance of really large numbers of n. Why this matters is if you're running a website, right, as your site grows, you need to know, will your operations, will the processes that you have, will they handle those types of inputs? You might have an algorithm that analyzes a photo to try and see, is there a dog or a cat, or classify it in some way. That algorithm might work on really small photos that are like 1 or 2 megapixels. And then as smartphones get better and they're like 12 megapixels or 24 or 50, and there's like phones that have 100 megapixel cameras, right? Does that analysis still work on an image that is that large? Or might your flagship feature of being able to search through your photos intelligently on a phone just start breaking because the images are too large? And so how an algorithm performs on larger and larger inputs really does matter. There are a limited number of cases where some algorithms perform better as n gets larger, but we're not really going to consider those. They come up a little bit in CS10. But in general, our orders of growth as an approach works really, really well. I'm not going to go into this table because it's just sort of a lot of examples. But on a typical computer, for something like searching through a list of numbers, even with small amounts of data, the orders of growth doesn't matter too much until we get to things like exponential functions, where if we talk about the amount of time that it takes when something grows exponentially, when something says like that's exponential growth, what they really mean is it is explosive, it grows incredibly quickly. We could even see that if we look at these last 3 columns, that things take a very long time. And at some point, this chart just says very long, because if you get past like 12,000 years, you can assume that your algorithm, even if it will eventually complete, is just too slow to be useful. So we're going to generally avoid exponential functions, but we will actually come back to a few of them in a little bit. We're going to continue this on Wednesday, since there are a lot of questions in today's lecture. But the main part here that we're going to look at is how do you determine, without just running through the amount of time, how long things take. So what we're going to try and do is build an intuition for analyzing code. And the first thing to think about is our number in a list? How do we approach this without running a stopwatch, without using the snap timer, that this is a function which runs in linear time? And when we're doing this, we can think about all the things that are a function of the length of the list, right? We've been saying as this list gets bigger and bigger and bigger, which of these blocks is really affected by that? Well, we have a for each loop for each item in our list. Well, this block is clearly affected by the length of our list, because if our list is 10 items, we have to do 10 iterations of our for each loop. If our list is 100 items, we have to do 100 iterations of our for each loop. Inside here, we have if number is equal to item report true. That's one check for every single item of our list. At the end, we have a report false. That may happen if we get to the end. But in this function, we only have one thing to consider, which is pretty nice, is that our for each loop is doing one action for each item of our list. And so that suggests that as our list grows larger, this function grows in a linear sense because what we have is every time we add 10 items, we do 10 more iterations of our for loop. And that's the kind of relationship that we're looking for. If our list goes from 100 to 200, we have to do twice as many iterations of our for loop. However, there are a lot of different algorithms. So we're going to do this question, and then we'll leave it here after this. So this should be question, let's see, which one is this on the grade scope? This should be 7. This is 6 on Gradescope. So question 6 is asking us to consider an algorithm where we're finding if 2 people, let's say in some list of people in the room of people have a shared birthday. For each person in the room, we're going to then go over for each other person in the room and say, if person X and person Y have the same birthday, we report true. If we get to the very end and we haven't reported true, we can then report false. So take a moment and think about, as the number of people in the room grows from, let's say, 5 people to 10 people to 100 people, what does the order of growth of this function look like? And this is question 6. All right, we'll give a few more seconds, 30 seconds or so. Let's see. All right, so this one is definitely tricky, and after this, we'll just take some additional questions. But this one is a quadratic operation, and if we were to write this out in Snap, what we'd see is we might think about how we could implement this. So if we say for each item, or for each person in a list, X, for each other person in a list, in that same list Y, how many comparisons do we have to do? Well, we have to compare X to everyone but X, so that's essentially n-1 comparisons, right? Because you probably can skip yourself as a comparison. For the second person, we have to compare them to everyone else in the list. So that's maybe perhaps n-2 comparisons because they've already been compared to the first person. The third person, right, we have to do n comparisons, but n-3 now. And so this is one of those cases where the mathematical intuition will take some time to build, but we can formalize this to say this is n-1 times n conditions that we'd have to build. And if we were to think about this in the case of a for loop, we might do something like for each item in our list, and then say for each item again, or we might actually say, no, we're not going to, I don't want a forever loop. We might do something like for each item I to n, and we might start an inner for loop at our second item. So we'll keep it, we'll revisit this on Wednesday. If you haven't had a chance to do the algorithmic complexity lab, I'd make sure to do that. But what we're looking for here is that operation where for every single item, we actually have to repeat that process all over again. And so things that start to look like nested for loops, in your mind, you should start to think, that becomes quadratic because we have to do something n number of times and do n number of times again for something that's like that. So we'll do a couple more examples on Wednesday. If you want to get ahead and continue looking at the slides, you can do that. And yeah, this is a pretty packed lecture, so I'll take questions for a couple minutes before I have to head to the next meeting. And we'll definitely have a lot more time for questions on Wednesday. Thanks, everyone. Thank you. Slides should be on the website already, right at the top, and then they'll be linked on the calendar later. Thanks, everyone in Zoom.